What?
All right, here we go. Okay, first big idea. Raise your hand if you can remember from the previous unit. If I have an integral, remember the words we're using in our classes, when there are limits we call it an integral, no limits, antiderivative, even though you will hear people use those words interchangeably. If I'm integrating velocity, now I'm just making up a number so we can discuss more easily. If this turns out to be 8, please raise your hand if you can tell me, what does the 8 represent? Overhand. You can talk to each other, I don't care. What does the 8 represent? Hands up. Hands up. Now, hey, look at me. You have to listen really carefully to the answer because it is common to get mixed up on this, and you just can't. There's 108 points possible on the AP test. What I'm reviewing here is about 30 of those points. Okay? So listen closely to the answer. Correct your thinking if you're thinking incorrectly. So Emma, what does the 8 represent?
The change in position of the displacement over 0 to 3 times.
Perfect. Perfect. I'll say it back. The velocity would be the velocity of some moving object. That object would have some position at time 0 and a different position at time 3. The 8 represents how different those two positions are, or displacement. So hands up if you knew that. 2 points. Okay. The fundamental theorem says there is another way to write what displacement, like another way to calculate the displacement. I cynically say it's the 3rd grade method because you could teach it to a 3rd grader. You don't have to know calculus at all. Like, what is the other common sense way to figure out how different is the position at 0 versus the position at 3? Hands up. This is 30 points on the AP test, this idea. 30 out of 108. What's the other way, Callie? Okay, raise your hand if your hand was raised, and you would have said that. You gotta see if you knew it. 2 more. Okay, 3 for Callie. This is just review of the fundamental theorem. Anyone want to talk more about this? Awesome. Okay, hands up again. What's another symbol that looks much like this, but not exactly, for the velocity of the moving object? Don't overthink it. It's really simple. Looks a lot like this symbol, but it's not quite that symbol, but it's really similar. What's the other symbol for the velocity of a moving object? So, Mallory?
X prime of t.
Oops, not 8, sorry. Okay, please show me your hand if your hand was raised, and you would have said that. 2 more. As I mentioned on the test, regarding the test, a score of 88 or higher will result in an A at the end of the term. And so I am trying to give out a bit more extra credit for the rest of the term to make sure that if you have that 88, you can get that A. So hence the little extra credit at the beginning and things like that. Okay, so the fundamental theorem says this. Question. Okay, this is how the fundamental theorem applies to velocity. But the fundamental theorem applies to any function. Even a situation where there is no story, the theorem still applies. So in general, I can write the theorem like this. Question? Pretty good? Okay. Because I can write the theorem like this, this provides a way to evaluate an integral without your calculator. or without like a Riemann sum, or without approximating. This provides the way to calculate the integral perfectly, like no error whatsoever. We talked about earlier that integration is simply these two things multiplied together, and the smaller dx is, the more perfect the integral. Nodding is helpful, thank you. The fundamental theorem says there's a way to compute the integral as though dx were truly infinitesimal. And the way we do that is noticing the relationship between f prime and f. So raise your hand if you can tell me, how is f prime related to f? Don't overthink it. Hands up. I just want you thinking, not just listening. Like, what's the relationship, Josh, between f prime and f?
F prime is the derivative of f.
So just say that the other way around.
The derivative of f is f prime.
I did bad. That was my bad. Let me say it back. You'll get it. That was my bad. That's well done, though. 2 points for that. Actually, I can give you a ticket for that. That was really good. So you said, so say it one more time. Either way, doesn't matter.
The derivative of f is f prime.
Good. So f prime is the derivative of f. When I say backwards, what I mean is, so you say f prime is the derivative of f. Therefore, f is the antiderivative of f prime. No worries. Does that make sense? Yeah, that's a bad question. Okay, that's, look, knowing that statement and the fundamental theorem, that's how we can find the value of an integral without any error at all. Because we can find this integral's value by finding the antiderivative of f prime and then simply using that formula here. That's what we're doing on this pink worksheet.
Great.
The excitement is overwhelming. Nick's like, great. One of the most, sorry, I have to be cynical. One of the greatest discoveries in the history of mankind. And Nick's response is, great. I'm not kidding. Like thousands of years, no one figured that out. Finally, Isaac Newton comes up with it. Great. Okay. What's hard is, hey, I think you'll understand this, but what's hard is people can't see the connection because there's many steps in between. But literally, cell phone communications, like all the communication systems that we have, the internet, flight, right? None of that is possible without this. Like just impossible. It would have never happened. We would still be horse, buggy, yeah. So. Moving on. So, you know, great. Okay.
So great.
All right. Clear this off here. So, look up here. So we now have a third way to find the value of an integral. In the previous unit, you learned two methods. One method was just pick up your calculator and type this in. You can still check your work that way. It's fine. Although this has the answers in the back, so who cares? Second method you learned for calculating an integral was Riemann sum. Now you have a third method. Since no calculator is available on this worksheet, you can't use a calculator. You look at this problem, you say, oh, got it. I need to find the antiderivative. Once I have the antiderivative, I'm going to evaluate that antiderivative at 3 and 0, and then subtract. That's how we find the value of the integral. Okay? There's some notation that will help with this, so we're going to work on this one together. But that's the big idea. Wave at me if you need me to say the big idea again. So, you look at the problem, you go, no calculator. So I can't do my easy way. It doesn't say to do a Riemann sum, so they are expecting you to use the fundamental theorem. Which means you think of this, it doesn't mean this is technically f prime, but it's good to think of it that way. Think of this as being f prime, you got to go find f. Once you find f, you're going to plug in a 3 into f, calculate that, plug a 0 into f, calculate that, and subtract them. Or think of it as velocity if it's easier. This is the velocity. You got to go find the equation for position. Once you have the equation for position, you can subtract those two equations to find what the value of the integral is. Okay? So clear this off. All right, next little hint. The square root freaks people out. I want to show something that hopefully will make you say, oh, not a big deal. Seriously. One of your green sheet rules says this. The derivative of the square root of some function is equal to 1 over 2 times the square root of that function multiplied by the derivative of that function. Raise your hand if that feels very familiar. Point for the exercise, good work. Look over here. Hey, remember what's happening when we're finding an antiderivative. So when we take the derivative of the square root of something, we end up with 1 over 2 times the square root. Okay? So that's what's happened here. We've taken the derivative of the square root of something, and that's why we got 1 over the square root. Okay? So it's really nothing that's that big a deal. We just got to go backwards. Okay? One thing that always helps is with a square root in the denominator, it's always easier to move it to the numerator. Just memorize that. Make a flashcard if you need to. It's always best just to move it. So before I do anything else, I'm going to write that this is equal to integral from 0 to 1/2 of 2x multiplied by 1 minus x squared to the negative 1/2 power. Because square root means 1/2 power. So moving that 1/2 power from the denominator to the numerator, I get negative 1/2 power. The rule is this. Let's see, we have 2x over 1. We also have 1 all over square root of 1 minus x squared, which means we have 2x over 1, 1 all over 1 minus x squared to the 1/2. The algebra rule says if you have 1 all over anything you want to any exponent, that's the same thing as same base, and then just multiply the exponent by negative 1. So, are you okay that this is this?
I am now.
Good. That's straight memorization. Root means 1/2 power. Straight memorization. No different than long ago someone told you that was A and you don't say Y anymore, you just say it is. That's the same thing. It really is no different. Does that make sense? Now I can use this property right here to rewrite this like so. 2x over 1, 1 minus x squared to the negative 1/2 power, all over 1. So that's how I got from here to here. So you just don't have to write out these steps. This is just so you can see it. Something's bothering
Oh,
you.
you're just writing on the steps?
I'm just,
That's still
I
not
wrote,
integral work.
yeah, like I wrote this, and a few people gave me this really terrible
like-
look and got
I was
sick.
just confused
And
where the...
so I was showing how I did that. So,
Got it.
yes.
That makes sense. That just disputes me.
Anyone still need this? Erase that. Okay. So when I look at this, I think this is my f prime. I need to find the f. So I need the antiderivative. That does not fit in your rule on the pink sheet. I can't distribute the 2x because this negative 1/2 power. So what I do instead is I notice that I do have 2 functions being multiplied. Hence, U-substitution is a good choice. So the 2 is a multiplying constant. I'm going to pull that out. As I look at the 2 multiplying functions, the first one is definitely something to a number, and the number is just 1, and the something's just x. So one possibility is u could equal x. So again, make sure you're doing your work in 2 columns here. But u equal x is never helpful, so skip that. The other of the 2 multiplying functions is something to the negative 1/2. So the something would be 1 minus x squared. So following the U-substitution process, I differentiate both sides. Always note this. If this says dx, this has to say dx. I don't want to go faster than you can write and think, so let's pause for a moment. You don't want to talk about it again differently. You want me to repeat something? Questions? So I end up with du dx is simply negative 2x. Okay, when you're doing a U-substitution, you check for to make sure that it's going to work. Here's how I know. I have 2 multiplying functions here. My choice of u came from this multiplying function. Therefore, the derivative of my choice should be this function. Other than this can be 1 and this can be negative 2, the multiplying constant doesn't matter. So it's going to work.
So on the buff packet, it had problems like this, but then the x was had an exponent.
If there's an exponent, it doesn't really change my thinking at all, because I still say this is a function that is of the type something to a number. So my choice for u would have still been x.
Right.
And then there'd be some other function. In fact, let's jump to it real quick. Which number are you thinking of? Find one.
Number 14.
I'm just going to go back to the beginning 1 second. Stop that. Should I have 14 listed? Everything but 14. There we go. Okay, so the hundreds of multiplying factor, I pull that out. So this is definitely something to a number, but the something would have been x, so that didn't work. This is also something to a number, so I choose that something. Good so far. When I take the derivative, I get 20x to the 4th, which is a perfect match because I don't care about the multiplying 20. It still matches the x to the 4th. Is that your question? Yeah. 2 points. Anybody else? Cool. Don't have a video on 14, but anyway, there's others similar. Look up. Look. I can't remember if I mentioned this last time or not. U-substitution is the chain rule backwards. Okay, the chain rule part of your derivative rules is the following words. Like when you're doing this, you say to take the derivative of the square root of 1 minus x squared, I'm going to take 1 over 2 times the square root of this something multiplied by the derivative of this something. Okay, the fact that I'm using the word something is important because we're trying to undo this. Like when we're finding the antiderivative, we're trying to work backwards from the chain rule. And that's why this pick here, I keep calling it the something. I joked about the movie, U is the something. Okay? It's because of this rule. When you take the derivative of this something, you're going to get negative 2x. That's what we got here. That's why this has to match. Don't worry about the constants. That can be easily fixed by factoring. But that's why we want this matched, because it's a result of the chain rule. This is the result of taking the derivative of something And when we took that derivative, we had this little part of it that created that little piece. And that's why we want this derivative to create that piece again. That's what we're checking for. Right? Questions? Awesome. And I erase the blue. Okay. So everything's going to work, so now I can start making my substitutions. So this is equal to 2. Oh, we have one new step. When we are finding antiderivatives on the buff packet, we switch to an antiderivative that uses u. We find the antiderivative, these symbols disappear, and then we switch back. Okay, when you're doing an integral with U-substitution, you do not switch back. You just stay with u. So you change everything and you never go back. So these limits, these are values of x. This is x equals 0 and x equal 1/2. I'm going to change them to values of u because I have a formula here that tells me how to do it. So I'm going to write down u equals 1 minus 1/2 squared. Because this x is 1/2, the formula says u equals 1 minus the x squared. So u equals 1 minus 1/4 or 3/4. Question? Oh, please, Hannah.
Wait, how does the x one help?
So when you see an integral, we haven't written this for a long time, but these are actually values of x. The integral is telling us that we want to do this computation for every x between x equals 0 and x equal 1/2. We're solving the problem with U-substitution. So we're transforming all of the x's into u's. This formula tells us how. So I simply plug in that x. 1/2 squared is 1/4, and I find that the u value would be 3/4. 2 points, please.
Does it matter which x you plug in?
We're going to do both of them. So it doesn't really matter which one you do first, because we have to change them both. 2 points for Jane. So now I have this. So now I have, when x is 0, u is 1. You don't have to write u equal, that's just me emphasizing the change. So the integral looks a little funny because they switched places, like the higher is on the bottom. But you can't control that, so just leave it. When x is 0, u is 1. When x is 1/2, u is 3/4. Pause for questions. Okay. It may look a little weird, but it really is a very straightforward process. You're just using the equal sign. You're just transforming from x to u, and you don't go back. Some teachers teach to go back. I don't like that because the AP test is going to make sure you know that you don't have to. If you learn to go back, you don't learn how to answer a few questions on the AP test. So, all right, I'm going to put a u in place of 1 minus x squared. I find it easiest to put that first. So I'm going to switch the order here because multiplication doesn't matter the order. That should be a positive. No, negative, my bad, sorry. That's my mistake. That's negative. So I plug in that. I still have x dx. Questions? It helped somebody yesterday for me to help them understand that here's where we are solving the problem. Here's where we are calculating all of the substitutions that we need to make. Okay? So these two things don't, they connect together, but they're separate ideas. Right here, I need to use this to figure out how to get rid of x dx. So I'm going to, down here, change color. I multiply the dx across. And then I divide both sides by -2. So I get -1/2 du is is equal to x dx. So in place of x dx, I can place negative 1/2 du. So this becomes 2 integral from 1 to 3/4 u to the negative 1/2, and then du divided by negative 2. Question? Please, Jane.
How did you get the negative 1/2?
So are you okay here?
Yeah.
So I multiply both sides by dx. So are you okay to here? Then I'm going to divide both sides by negative 2. But dividing by negative 2 is the same as multiplying by negative 1/2. 2 points. You lost me up a little bit. Please.
Yesterday I was a little confused when Summers showed me. So instead of having x dx, I moved x over, so I have 1 over x.
There are different methods. You can choose the one that feels most comfortable to you.
Okay. So but that still works like that.
If she showed it to you, it works. No
I was just
doubt.
making sure. Like,
Oh no, if she showed you, it works. I like this way better, just personal preference. But no, you're free to do that. Anybody else? Please.
Wait, so what exactly was the reason for changing the limits? I'm trying to, maybe I just don't know.
I'll show you in a second. It'll make more sense in a moment. Everybody good in here? Okay, the negative 2 is a multiplying constant. So that can come out. 2 divided by negative 2 is negative 1. So now I have this. Don't let me forget your question, Matt, but I believe it will make more sense in a moment. So other than changing the limits, all of this is exactly the same as the buff homework. Like nothing we have done is different at all, other than changing the limits. Pretty good? Okay, I'm going to make a copy so I can get to the next part. Come on, board, do your thing. There we go. Okay, I'm gonna erase everything but this. Are we good? I can always go back if we need to. I just made a copy of the page. Okay, so here's the answer to Matt's question coming up. Move this up a little bit higher. That's really silly. That didn't work well at all. There we go. Thank you. Okay, we can now use the rule, because this is just the power rule on your sheet. So this becomes, don't forget the equal sign, negative 1, u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. Okay, points for the whole room. This, if I were to put the x back in, like the substitution, we have the substitution u equals 1 minus x squared. If I were to plug that back in for u, please raise your hand if you can tell me, how would this function be related to, not the integral, just this? This is not a new question. It's the same thing we said earlier in the class. If I put, hands up, come on. If I put this in for u, how is this function relate? You can't lose track of the meaning. 30 points out of 108. How are these two functions related if I plug this back in? How are they related? Hands up, come on. How are they related if I plug it back in? You're over to talk together. You gotta get more hands. There we go. Hands up. Come on. Show courage. My young Padawans. That was dumb. Look out. Look out. Colby, how are they related? Perfect. This is the derivative of this. Pointing helps me. This is the antiderivative of that. So in symbols, I like thinking of it as this is f prime, this is f. How many knew it? 2 points, 3 for Colton. Is it okay? Remember the fundamental theorem. Fundamental theorem says we can calculate this integral of f prime by finding the change in f, like how different are the values of f. Okay? Now, because we changed the limits, it's a shortcut. We don't have to go back. We don't have to plug this back in. Mathematically, it's perfectly equivalent. So all we have to do is say, here's f. Let's plug this into f. And then let's plug this into f and subtract them. It's the fundamental theorem. Question? When do you want me to repeat that? So there's a symbol you're going to use. It's the bar. So write the bar like this. Okay, the bar has no name. I Googled it. There was no name for the bar. It's just the bar.
Can we name it after B?
We are going, so here's how this is what we do. Look, you got to make me a sign though. I got a sign.
All right.
It's got to be nice so it lasts for years. So when we are finding the value of an integral without our calculator, we're using the fundamental theorem. So we think of this as being f prime. We have now found f, and now we need to nick it. Okay?
Yeah.
I don't know if that sounds right or not, but
It works.
whatever. Okay, 1 year it was Frank. Okay.
Here it was free.
It's true. This isn't the first time somebody suggested naming the thing. We can Wilson it if that's better. You know. Wilson it. So Nick sounds a little harsh.
I like Frank more.
You like Frank? So Nick can make a sign. Nick Thompson. Nick. My apologies. Nick Wilson. No, whatever. Franking it. So you put a 3/4 here. You put 1 there. Please make sure you're using proper notation so you don't lose points on the FRQ section. Okay? So now, this is kind of messy. It does help if we clean this up a little bit. The bottom is positive 1/2. Dividing by 1/2, same as multiplying by 2. -1 times 2 would be -2. U, this is just u to the 1/2. Sweet, that's square root of u. Remember, what is that? What's that? What's that? Q. That's it. That's whatever. Rough day.
I forgot it was -1/2.
So this is positive 1/2.
Hold on, sorry, I forgot it was -1/2 plus 1, which makes it.
There you go. So then we Wilson it. Okay. I can envision the poster. It's awesome. You go online and you get a picture of Wilson the volleyball from the movie Castaway. And then you make this nice. This has got the face and everything. And Wilson says, "Do this" or something. Never mind. Whatever.
I like Frank. It's like ballpark. It's like a stick.
Oh, ballpark Franks. There you go.
It's like a stick.
Commercial. Okay. This is f, right? The fundamental theorem says we take f and we plug in the 2 values and subtract. So the next line, you do this. -2, square root of 3/4. That'll make you puke. Square root of 1's nice. That was easy. Okay. Yes, I'm just emphasizing that we are using the fundamental theorem. So this is our f prime. We've got to find f and then subtract. So because of the U-Substitution, we just changed it. Anybody else? Okay. So now, oops, wrong button. So now we have this going on. Okay, look. You're just going to have to memorize. The square root of something divided by something can be split into 2 roots. You practiced this years ago. It's been a while. Just have to remember. If you have the square root of two things multiplying, you can split. Adding or subtracting, you cannot. So this becomes negative 2, square root of 3 divided by square root of 4. Subtract, plus, as Micah said. Root 1 is just 1, so like that. The best news is this. On the written section of the AP test, you stop here and don't do anything else. And you'll get full credit. On the multiple choice, we do have to find our multiple choice answer. Okay? So this is where I honestly, like I know the next step is this. That becomes 2. These can divide, so you end up with negative root 3 plus 2. But I don't know if that's the answer if we did something. I think that's the answer. Is there a 2 minus root 3 answer? Yeah, I checked the back, but I'm 99% sure.
Yeah, that's right.
Okay. Kind of a funny number, but if this were the velocity of a moving object, this would be the displacement for that time period. If you type this in your calculator, you get this answer. You type that integral in your calculator, that's the answer. They'll give it as a decimal, but same thing. Question? Holy shit. Okay. Is that inappropriate?
I can't wait to rewatch
That was looking
Chew.
What a chew.
What a chew. Okay. That feels like the wrong. I thought you say chew when like something goes wrong. This all went right. I don't know. I don't know how to speak. Oh! Hold on. Hold on. Hold on. Ticket bequeathing ceremony. Look. Okay, look. When you're when you're finding an integral without your calculator, you have to find the antiderivative. That's this. Jane correctly remembered that we usually, when we find the antiderivative, we say plus a constant. Right?
Yeah.
When you're computing the integral, however, you're going to take this, plug in 3/4, minus this again, plugged in 3/4. So what's going to happen is, just give me a second, you have the C, it's going to be right here. Then when you plug in, let's move this out a little bit. So it's minus, it would be negative 2, square root of 1, plus C. But all of this is being subtracted, so you have to have a parenthesis there. With me? So when you distribute the negative, as Micah said, this becomes positive. That C becomes negative C, adds with that to become 0. So whenever you're finding an antiderivative, and then you're computing, the C doesn't matter, because it will always subtract out anyway. So no one ever writes it. Does that answer your question? Anybody else? Anything else here? Awesome. Save that for future